All right, let's take a look at a specific example of refraction and where Snell's law just might fail you. So we'll start with an example question. In this case, what is the angle of refraction when light travels from water to air if the incident angle is 55 degrees? So if we start with Snell's law, N1 we'll say is the first medium will be water. So N water, sine of the angle in water should equal N in air, sine of the angle in air. And so now we should be able to put our values for each of the quantities in here. The index of refraction of water, if you look it up in your table that's supplied in your booklet, 1.33 multiplied by the sine of the angle of water, incident angle. So that's the sine of 55.0 equals the index of refraction in air, which is 1.00, multiplied by the sine of the angle in air. And there's our unknown. We're looking for the angle as it leaves the water and goes into the air. Let me get my calculator here because something interesting happens when you go to solve this equation. First of all, whenever you, like I have, just turned on my calculator, make sure you're working in degrees. And now let's put the values in. So on the left-hand side, I have 1.33 times the sine of 55. That gives me 1.089. Divide by 1 to move the 1 over. And so the sine of the angle in air, if I just write this out, the sine of the angle in air is equal to 1.09. And now something interesting happens when I take the inverse sine of that. My calculator gives me an error. In other words, it cannot tell me an angle when the sine of the angle is 1.09. And this is not a big surprise. If you think about what sine really is, the sine of an angle is always opposite over hypotenuse. And as you probably know from studying triangles, the hypotenuse is always greater than the opposite side. You can't have a right angle triangle and have a hypotenuse that is smaller than the opposite side. And therefore, this ratio of opposite, smaller number, over a larger number should always be less than 1. So the sine of the angle is always less than 1. So what we have here is an impossible situation, one in which you can't have light at an angle of 55 degrees in the water going into the air. But you might ask, what happens if you try that? Well, let's try it out. So I have here a simulation. Let's move my calculator out of the way. Take a look at the simulation now. So I've set up exactly the scenario we talked about. Here's the top material up here is going to be my water with its index of refraction of 1.33. Bottom material is air, index of refraction of 1. And I'm going to shine the light at progressively larger and larger angles. So I'll put the protractor there. You can see what's going on. So if I shine it in at 0 degrees, and you can feel free to calculate some of this, but if it goes in straight in at 0 degrees, it's going to refract at 0 degrees. As I increase the angle to about 10 degrees or so, so right around there, 10 degrees is my incident angle. My refracted angle is 13 degrees. Now watch what happens. As I increase my incident angle to 20 degrees, my refracted angle is 26. It's always greater. And in fact, it's getting bigger at a more and more rapid rate. Notice as I increase this by another 10 degrees, I get more than 10 degrees increase in my refracted angle. And so you'll see that eventually I get to a point here. You can see it happening, increasing my incident angle, increasing my refracted angle. And at some point, something gives. So right around here, I have an incident angle that's giving me a refracted angle pretty darn close to like 90 degrees. And then what happens when I go beyond that? Somewhere around the 50-degree mark, once I go past that and I get to say our 55 degrees that we were looking at in that question, you'll see that that angle no longer provides us with a refracted angle. All we get is a reflected angle. So this is a phenomenon known as total internal reflection. rather than have light partially reflected, which it is here, but mostly refracted, we get nothing but the reflected angle. So we've gone past something called the critical angle, that point at which before that we were getting refraction, then after that we get no refraction, and somewhere in the middle is this magic breaking point we call the critical angle that gives us exactly a refraction of 90 degrees. So the reason that you will get an error in your calculator once in a while is because you're trying to calculate for situations in which you've gone beyond what we call a critical angle. So, couple definitions. Critical angle and total internal reflection. What are they? Well, by definition, the critical angle is the angle of incidence that produces a 90-degree angle of refraction. So, getting back to that example, if I have a boundary between two mediums here, let's try this a little differently. If I have a boundary between two mediums, let's say I have on one side water and one side air is what we used before. So on this side, if this is the water side and this is the air side, as I shine light at progressively bigger and bigger angles, I get bigger and bigger refraction. So there is this magic point where we get an incident angle right here. Let me give myself a normal line, something like that. So if this represents my normal line, I shine light in at such a way that the incident angle right here produces a refracted angle that goes exactly 90 degrees to the surface. So I'll do it this way. So I end up with this refracted angle that's exactly 90 degrees. That's when you know you have your critical angle. So let me label this. The refracted angle right here, angle of refraction equals 90 degrees when we are at this critical angle. So again, critical angle is the angle of incidence that produces a 90-degree, so it comes in at this angle, it gets refracted straight this way, 90 degrees. That leads us to this next definition. If the angle of incidence is greater than the critical angle, total internal reflection will occur. So if we go beyond that, let me use a red line to say if we shine light at this angle greater than the critical angle, then we get instead of getting refracted, we'll just get a reflected angle. And that's what you saw in the simulation. So a couple things that are worth noting though, critical angle and total internal reflection only occur, let me get rid of some of this stuff so I can write. You need certain conditions in order for this to occur. They only occur, for example, when you have a wave, only when waves travel from slow to a faster medium. Okay, let's take a look at the simulation just to be clear on this. It can happen when we have, let me get rid of the protractor. It can happen when we have small angles going from, okay, so we're going from slow water to fast air. And as we increase the angle, the refracted angle gets bigger and bigger at a faster rate until we get to that critical angle, and then we get total internal reflection. But if we switch the scenario, put the air as our first medium, put our water as our second medium, because the refracted angle is always towards the normal. In other words, the refracted angle is less than the incident angle. We never have to worry about, we never experience this critical angle or total internal reflection. No matter how big we put the incident angle, we will always get a refracted angle. So, getting back to this important note, critical angle and total internal reflection only occur when waves travel from slow to faster mediums. So somewhere where the index of refraction is greater in the first medium than it is in the second medium. So happens from water to air, will happen if we go from glass into air. We can also get a critical angle and total internal reflection. And it all depends on how much we speed up, or sorry, in this case, how much the the wave speeds up how much it refracts. All right, so just one calculation to just get an idea of how we can use this critical angle idea and understand the idea of critical angle to solve a problem. The question is, what is the critical angle of a diamond-water interface? In other words, if we have a boundary between diamond and water, so let's say, for example, you dropped your favorite diamond into the water. We'll make it a nice little cube here. And light were to travel from the water, so we'll make the water on the outside and the diamond on the inside. So out here is water, inside here is the diamond. And so we picture this light traveling again. It's got to go from the slower medium to a faster medium. So it doesn't tell us that here, but you know, if we understand the idea of total internal reflection and critical angle, we want a situation in which this wave travels, or this light travels from the diamond into the water, and it does it in such a way that the refracted wave, as measured from the normal, you get this phenomenon that we talk about, the critical angle of incidence in going from the diamond into the angle in water, which is going to be 90 degrees. So that's the picture we have of this situation. Let's see if we can't solve for it once we understand that. So again, from diamond, it has to be from diamond into water. So we'll set up Snell's law just this way, index refracted in diamond. We'll go index of refraction in diamond times the sine of the angle in diamond is equal to the index of refraction in the water times the sine of the angle in water. Now, if you look it up, index of refraction for diamond, the index is equal to 2.42. Index of refraction for water is 1.33. So in this case, we're starting in the diamond with its 2.42 index of refraction times the sine of the angle. This is what we're looking for, the angle in the diamond. That's the critical angle. Index of refraction in water is 1.33 times the sine. And you might say, well, what's the angle? Well, that's this angle. It's 90 degrees. So sine of 90 degrees. So if we pull out our calculator again, take a look. In this case, we'll go try that again, 1.33 times the sine of 90. Now let's hit enter and just see this. Sine of 90 is 1, so no surprise, it's 1.33. Move the 2.42 over here by dividing by 2.42. Now we have the sine of the angle, in this case the critical angle, 0.549. So I'm feeling good that we'll be able to solve this. Inverse sine of that, 33 degrees. So the critical angle is equal to 33.3 degrees. In other words, if this angle is 33.3 degrees or greater, we will get total internal reflection. Well, I guess at 33.3, we get refraction at 90 degrees. Less than 33.3, we get refraction, no problem. Greater than 33.3, we get total internal reflection. So the math is not any different. We still use Snell's law to solve for critical angle questions. What is different is this understanding that the critical angle is that angle that produces a refracted angle of 90 degrees. Real quick again though, remember, in order to get critical angle, it has to be going from a slow medium to a fast medium. We experience the critical angle when we get a refracted angle of 90 degrees, and that leads us to this idea of total internal reflection, that this wave will stay within that medium once we're past the critical angle. So here it is, going from glass into air. Now we're beyond the critical angle. Now we're less than critical angle. Critical angle is that one special angle that produces a refracted angle of 90 degrees.